Please fire the later. Use like a golf club.
She hasn't realized. Well, and all that happens, right? I was watching one before.
Yeah, face, type, face. All right, so. Which one do you have? Let me see real quick. That's what I
That's all I got.
Well, this is overview of biostats, so this is still like let's just pick up. So
Make sure you've got everything that you need on.
okay, so hang on.
You don't have everything you need to.
Wait 1 minute, just bear with me. So when you emailed me a week ago,
Yeah.
you sent me 2 files that
Right, is it the second file?
yeah, second file. If you could make,
Okay.
yeah, no, I can get to it. Just wait 1 minute. I can get there. What I need you to do for me is to make copies of both of those presentations for them.
Okay.
All right, and if you come here, you see read an introduction to statistical power and power 2. Those are today. So if we can make those, and I'll go slow. Power 1 and power 2. Handouts are coming, but we're gonna start. So and what I'll do is I'm gonna kind of blend a little bit that I did not get through last week into this, but I'm going to say something and it's going to sound really crazy, and it's not. Would you like to see the presentation that's called Overview of the Department's Finances? It's right there. You see it? FY16 _2. You can tell you all about our biostats finances if you wish. But we're going to talk about statistical power, because I'll be very honest, that's the only reason people talk about it. Other than trying to get the data analyzed, most of the time people are very worried about statistical power. And so today, nope, that's the wrong handout. New handouts are coming. Just a minute, I will go slow, but new handouts are coming. Because there was a little bit of confusion that they didn't let us go ahead and launch into power. We're going to deal with power today, just unpack it, because if you've got the fundamentals from last week of, what's a type 1 error rate, what's a p-value, beyond a reasonable doubt, all of these concepts, I find that almost where every research grant I design, power is misunderstood. And we go about it in the wrong manner. So what I was going to do today is demystify it, show it to you from the way it was originally produced, and then talk about when we are working and designing a study, what should the investigator start with? What should the investigator have before trying to talk to the statistician? How soon should you be talking to the statistician? And is power really the place to begin? And the answer to that is, of course, no. Don't start there. You got to start somewhere else. So let's go through and we'll just talk about, like I said, power. So let's ask the internet access. Here's what I'm looking for. So when we talk about it, so what we're going to do really quick, to do power, I'm going to just start out with the most fundamental. Almost always people come to these is, let's compare two groups. What happens with two groups of means? We're going to talk about proportions. Why do? Is it two groups, two groups? Absolutely not. Never. It always, first rules remember today, it always depends on your outcome, not anything else. If you come to me and say, and you're going to laugh at this, people will stop me on the street. I'm walking toward lunch and people will stop me and say, how many people do I need to do this? Like, like I have it memorized in my head. And that's nowhere near the truth. I will have to say, look, why don't we set up time to have a cup of coffee? And first you tell me, what's the nature of your outcome? Are you going to classify people as, yes, they have the characteristic, or yes, they have a response, or no, they do not respond, yes or no? Are you measuring how long they survive? Are you measuring something continuous, like BMI? These all play in to the way that I have to approach it. So until we talk about the outcome, don't even bother to tell me how many groups. First, tell me the outcome. Tell me what you're trying to measure. And I'm going to say, this is your, remember when I told you that when they train you to be a professor, the first thing they try to teach you is tell them what you're going to say. Halfway through it, say it again. And then at the very end of it, say it again. At one point, the most important part of the power section is not the calculation. It's not the calculation itself. Okay? Is the power calculation ever correct? The answer to that is no, because you will see the very first word in if the statistician is doing their job, the first word in the power calculation is assuming. We have to list out a series of assumptions that justify the landscape of the calculation. If you submit a power calculation to a journal or to NIH that doesn't lay out those assumptions, your life is going to get busted. Not when I say busted, that's kind of hard. You're going to get a lot of questions, rightfully so, about what were the assumptions behind this. Okay? Back up, don't read that yet. Somebody define power for me. What is statistical power? What do you think it is? It is an assumption. What else is it? We can check the reliability of the what we find. Be very careful. That's the dangerous slope that NIH has been after for a long time, over the past 2 years. When I give you a p-value, it doesn't tell you any chances of reproduction. It just tells you about that particular data set, the data set you have at hand, and how compatible it is to a specific belief, such as innocence or guilt. The p-value measures how compatible that data is to a given hypothesis. Power is the future. If we do the experiment under these conditions and this difference exists, notice the two things, under these conditions and a difference exists, or something clinically relevant exists, then I have the following probability of finding it or declaring it significant. That's all it is. It is a statement about the future. That's all it is. And it's based on a ton of assumptions, typically. All right? So, give me another layman's well. I already kind of blew that, so I've already explained it. It's simply a description of, notice, possible experimental outcomes for which we are likely to declare that the intervention experiment works. All right? I use the word in there likely. Code for probability. That's all it is. It's a code for probability. So if I tell you I'm giving you 80% power, I have designed this study. Notice I use the word designed the study. By controlling the sample size, I've designed the study. And I tell you that you have an 80% chance, or the power is 80%, to detect a 2-unit difference between the groups, whatever the 2 units may be. What does that mean? What does that mean, mathematically? What does it really mean? It means that 8 out of every 10 experiments, if we could do this 10 times, the laws of probability say 8 times, you should be able to say, found it. It also says the exact same thing 2 of those times, you're rolling the dice. And there's a chance, there's 2 out of 10 chances that you're not going to see. Where you're going to, it's really there, but you're going to say, I didn't find it. Right? If it's there, you'll not be able to declare it significant. Or it can be written, and this is the thing about talking to a statistician. You can tell the number of years the statistician's been working by the way the grant power calculation is written. And I mean that right out of graduate school, I would write a power calculation as the 3 sentences. Here's the assumptions, here's the calculation, let me interpret it. I stopped it. Because I think that would be misleading. Because that's just one set of assumptions. What I do now is I'm trying to build a grid and say, this is the landscape of the experiment. If the assumptions are slightly off, how much do things change quickly so that you get a more complete view? But often I'll build the table to do this, to say, all right, these are the sample sizes, and you'll see on the grid just a series of sample sizes that would guarantee you would have 80% power if the assumptions in that column, in that row, are correct. And then I can go to another assumption in another row, so I can go to another cell and say, okay, and I can map out all the different combinations so people see the landscape. So what happens? I told you need 120. What happens if you got 140? How much did you, or where did your power go? What if, what if you're recruiting for a clinical trial and switching, you needed 40 per group? And unfortunately, you're sitting at 25. Are you in no man's land, or are you still safe? These are the types of things that you need to think about when you talk to statisticians. The statistician comes and brings you one piece of one calculation. You need to say, hey, can we do what's called sensitivity analysis? Right? It is not the first thing to be worried about. Please, here's your take-home message. Don't get obsessed with alcohol. Okay, I understand you got a budget. Got that. And I understand I impact your budget terribly by the sample size. I got that. But don't put the cart before the horse. The first thing that wins and loses every grant, you know what it is? Anybody been in the study section? You want the dirty secret when they close the doors? The win and lose will page 1. You write all these pages, but if page 1 doesn't convince them that that's a very important problem, it doesn't matter how well I write the power calculation. It doesn't matter how cool your technology is. What matters when you're working with power calculations and designing things and trying to get it through NIH, what matters is your hypothesis. How solid is the hypothesis? How relevant is the hypothesis? And to me, the hypothesis is all I care about. I can't do anything about power until I understand your hypothesis. You'll see why in just a minute. And it's right back to that concept. Now, When you come to consult with me and we sit down and we have a cup of coffee, you don't come in and say, okay, David, I think it's mu1 is equal to mu2 and mu1. No, that's not, that's my job to get it into Greek parameters. And that's my job. Your job is to say, David, we're going to have two groups. We're going to intervene and we're going to exercise them. We've got one group that they're after stroke. And I'll give you an example of what I had designed last year. Now go look it up. Without reviewing, so I won't tell you the question. David, this one of the biggest things about after stroke is loss of mobility, loss of balance, falling, breaking the hip. Now you've compounded it, as we all know, once you fracture the hip, now your odds of, once you have that hip fracture, the probability of your death goes way up really fast. So interventions to increase their stability. Okay, interventions to increase their stability. We're going to randomize one group to this and one group to that, two different ones, and we want to know, is one of these superior? Helping me understand that leads me immediately into, all right, now I know how to start designing and bringing it in. But it's the first thing you do is you talk to me about the hypotheses, and the first thing you worry about is defining your outcomes and what your scientific purpose is. Once you've got that, now it's time to find it. If you're having trouble defining it, it may be very worthwhile to sit down with a statistician and talk about it and lay it out and see how it should be structured. But that meeting is not to walk out with power calculation, or that meeting is not to walk out with respect to power calculation, but to come back in and set the measures. You expect in that meeting, if it's not fleshed out, for us to be writing it out and trying to solidify it so that everybody knows this is the way we go. Please understand that power calculation is not a guarantee of success. Even if I drive the power to 95%, not a guarantee of success. Two reasons. Even if I assumed everything correctly, probability is 0.95. The chance is, remember, every experiment has a chance of failing, even if everything went right, because you're using statistics. And statistics always include the chance of not declaring something. Always. And keep in mind, people, it's not an exact measure. Our calculation is a set of guesses. All it is. It's informed guesses, but all it's doing is laying out potential possible ways this could fall out. The way I like it when I introduce it to graduate students, if I talk to you about rolling the dice, giving the dice, we can build a grid and show the probability of getting a 2, and show the probability of getting something to be 3. All I'm doing is I'm building a grid like that and showing all the different possible ways that this experiment might come out and what our chances. Our chances of declaring something statistically significant. I always get ahead of myself. First things first, Pacific Games. I'm sorry. It's just the truth. Power calculations cannot start anywhere without the specific gains. Ever. Now you can say, David, you're tying this too much to grants. Okay, fine. Maybe I am. But even a paper has some form of a hypothesis behind it. And in this, please understand this. If you intend to report a p-value, you're going to report a p-value in that paper, then you probably should be talking to somebody about power. I was in this room 2 weeks ago with the table set up, and we were doing this consultation. And I had to go toe-to-toe with somebody who kept saying, we don't need a power calculation. We don't need a power calculation. We don't need a power calculation. And I pulled up one of the papers and I circled the p-value and said, are you going to report a p-value like this? Yeah? then I have every right to ask you your power. If you're reporting a p-value, if you're going to go there, you should consider what was your power. Even if you declared it to be statistically significant, you just talk about power. Think about what will be measured. Think of what observed changes of association would convince you. This third point, for those of you that are taking notes, put an asterisk by it. There are two things I'm going to ask you when we're in consultation, when we're meeting. And this is the one that trips everybody up. What matters? I took my stat in this one. Yeah, I know. But I have a huge family history. So I took my stat in this one. But when the stats were being developed, the question would come, what was a clinically relevant decrease in LDL? What would matter? You drop my LDL by 2 points. Should I be taking the pill? Should I be taking this drug? Well, what if you dropped it by 10 points? Now that's a bigger effect. You should hope that maybe my arteries would not clog as fast. But it's imperative that the clinician say what is clinically relevant. And please know this. Clinical relevance is not statistical significance. Those are very different things. Okay? All day long, I can find clinically irrelevant things all day long. The truth. I can design a study so big, I can find things that don't matter. So the best thing to start with is what matters, so we design the appropriate size experiment. And after considering these things, that's when you meet with the statistician, because these things are going to be coming up over and over. You should never expect to get into a power calculation discussion without somebody asking, what's the hypothesis, what's the outcome, what's the number of groups, what's clinically relevant? What is clinically relevant? Now you're going to say, dadgummit, David, that is terrible. How am I supposed to know what's clinically relevant? That's science. That's science. Science depends on clinical judgment. Medical practice depends on clinical judgment. All science does. Now, my advice to people is don't give me one. Give me a range. Say, David, it could be, some people might be convinced it's this small. Some people won't be convinced until we see something this big. Just give me the range. That'll help me build the table to enable a discussion. Okay? By the way, you're all quiet this morning. I know I didn't sleep last night and I've had way too much coffee already. Does anybody have any questions? Any questions yet? Doing good? Okay? All right, so talking about the hypothesis testing, let's go back to our jury trial from last week. How many hypotheses are there in jury trial? 2. Guess what? In almost every experiment we do, every stat problem, we're going to give you 2. Okay, but this is where it gets kind of really cool with power. All right? The research, remember, we've got the one that the research hypothesis is the one we won't prove. So we always want to prove the alternative. Well, excuse me, I should be shot on the spot. We would like to find evidence for this. We can't prove it. Probability. We want to be able to see if we can find evidence for the alternative, the H sub A. So we have 2 experiments. We have 2 groups. We're going to intervene. We're going to, I think my teaching example here is we're trying to shift BMI slightly. We're expecting one group to decrease while the other one pretty much stays constant. Well, here's the thing. And this is what I'm trying to get you to understand about clinically relevant difference. For me to do the power calculation, I don't have to worry about this. Whatever pairing you have there, you can make it 40, 40, 50, 50. I don't care. They have to be equal. This condition makes that statement true. Right? But when I go to power, you have to help me imagine a condition that makes this one true. That's your job as clinicians. Imagine me a situation where this one is true. Okay, well, I imagine 30. I'm going to set mu1 as 30, and I'm going to set mu2 as 27.5. And the question becomes, if this is the truth, what's the probability I'm going to declare reject the null, include the alternative? That's what a power calculation is. Now, here, I want you to imagine for a minute. Reason it out with me. What would happen if I said, oh, what would be the power if I said 30 to 25? Is the gap growing? The gap's growing. What happens as the gap grows? Let's just say that we have a big sample size. Suppose the gap's really big. Do you think statistical power is going to go up, or do you think statistical power is going to go down? The bigger the difference, it always goes up. Always. Big differences are easy to spot. Who discovered the Grand Canyon? We don't know. History didn't need to record that. It was pretty easy to spot. Okay? If it's a big difference, easier to get power. But let me ask you this. If I said 30 versus 29.9999, which statement is true? The alternative is still true. It's just a very small difference now. How hard do you think it is to design that study? Very hard, because I'm going to have to jack the sample size up very high to focus my microscope to find small differences. If I have big differences, I don't have to focus the microscope is big. The focus is my sample size. My ability to focus in an experiment is based on my sample size. Okay? So just keep in mind, your key job is to be able to help me understand what that difference is. Now, I'm doing a teaching example. I doubt a difference of 0.0001 is never going to be clinically relevant. But what I want is I want a range of clinically relevant. Okay? Now, does anybody remember from last week what a p-value was? Test, retest. Gosh, we gotta hate this. What's a p-value? More than a hunch.
Well, it's not standard. I remember you saying that it's just a number that somebody...
Okay, refresher time. Null hypothesis in a jury trial is innocent. Alternative is p-value is evidence, right? Right. The p-value is the evidence, and we need evidence beyond a reasonable doubt. And again, is the evidence evaluated under the belief that which hypothesis is true? The person is innocent, so you evaluate it under the belief the null is true. So I'm going to conduct my experiment assuming that this is true, but I want to know if this is really going on, can I get enough evidence to get over to this side? That's what power is asking about. So here's what really happens as a statistician. I think that's the next slide. Yeah.
Ask a clarifying question.
You can always ask a question.
Some of the confused because, for instance, we say power is 10 or 20%. Right?
One more time.
Power is a percentile.
Yes.
Right. Okay.
Well, it's not percentile. We're just putting it on a number scale 0 to 1. Or in a percent. So when I do a calculation, I will get a probability. I will get a number between 0 and 1. And when I say 80% power, it's a probability of 80. 0.80. If I say 95% power, it's 0.95. If I say 50% power, it's a 50-50 shot. Okay, go ahead.
So going back and you say, with a larger difference, having larger, or assuming the same patient.
Same number of observations.
Right, and you increase the difference between them, say your power goes up, decreasing and power goes down. what if the power is assumed to be the same? Then would you say that the number of patients you have is just a surplus of what you need? Is that basically the corollary of what we're saying?
Yes, and that's the catch, is if you fix the sample size and keep doing that, then what I'm going to do is either, quote, have more subjects than I need to achieve a specified power level, or I'm going to have two. And you're going to see in just a minute, there are really five components I have to put in the calculation. Here's the game. I will say, I assume this, I assume this, I assume this, and I assume this, and then allow them to solve for the last. You're going to see that. Part of that is the N, the sample size. Yes, sir.
So since power is about future, if I say about weather tomorrow, it's going to be between 30 and 90. I mean, I'm about 100% correct.
That's exactly right.
So what's the relationship with the confidence interval?
Oh, that's a great question. So, with regard to it, when we say a 95% confidence interval, that has very little to do with power now because you have a data set in hand. And you're teaching example. Once I observe the weather tomorrow, there's no need to talk about future probability. I know it. I know what happened. It's rain did. Okay? But once you've got the data set in hand, I'm able to say, this is the compatible range of values for the parameter that match this data set. In other words, this data set would suggest I should not anticipate something outside this range. Okay, I should expect that the probability distribution that generated this is within this range. That's all it's saying. Yes?
So following on this question, so the confidence interval also is a measure of the variability of the measured variance.
That's exactly right.
So that's also predicting the future. So if I know that.
But the catch is you've got to know your samples. Now, the reason it's not the future is if you think about what goes into a power confidence interval, I have a sample mean, which means I have the data set to calculate it. I have the sample variance, which means I had to have the data set to calculate it. I have the sample size of that data set. All of those things are known. The only thing that I'm doing in the power calculation, the only one, I'm projecting what the N may be and assuming the rest. So they are no longer assumptions. Right? At that point, once I have the data set, there are no longer assumptions. There's that right. Okay?
But sometimes you extrapolate from another data.
I do it all the time.
Right.
Not sometimes, almost all the time.
Okay.
But I use that as a gauge. And then I do my game of, that's just one day, that's just one published paper. Let's put some ranges around that and see what happens. Okay. See how sensitive, what I'm trying to do is how sensitive is my calculation to my assumption. If it's not very sensitive, I'm safe. I can say this, I can say to the subsection, even if I'm off a little bit of my guess here, we're still on safe ground. But if you see the polytron cracks, you know, God, you better be confident in that one. Things will change quick. All right, so then, I love this picture. I love this picture. Only a statistician can love this picture. Okay? So here's the catch. I want you to think about it. This is the null, and this is the alternative. When I'm doing a power calculation, now listen, if you get this, you're going to understand to a degree more than 99.9% of the people on this campus. You understand this picture, you understand power. You really do. What happens is I have an assumed distribution under the null. Back up. Okay? You see that this guy is centered on 0? See that guy? He's centered right on 0. Mainly because, what's the difference between those two means? 0. So I'm building that first bell on the assumption under the null. And what I've done is I'm putting, I get to have a type 1 error, the probability of rejecting if the null is true. But I set that to be no more than 5%. So I put a little bit of probability down here and a little bit of probability here. That's the guy I'm referring to in the green bars. Say, only when I get into this region can I reject and go to the alternative. This is what Naaman Pearson taught. Use a rejection region. If you get outside the green bars, reject. Well, what do you think this guy is? This is under the set of assumptions that you believe the alternative is occurring. And what has happened is by making a different set of assumptions, you've literally shifted, shoved the underlying distribution in a specific direction. And look, how much area is now falling beyond the green bar. This piece that's above the green bar is your power. Think about that. This is your power. You've got to get above the green bar. So you, by assuming that you're going to create a two, that this would be the power if you said we're going to separate the means by 2 units. You shifted it, and now I've got to use mathematics to calculate how much is in this wedge. That's power. Now think for me real quick. You make a bigger difference. Make it go to 4. What happens? It continues to slide, and more of the distribution is falling above the cut point. That's what I'm doing when I'm calculating power. I'm just saying, under this assumption, how far is the distribution getting shoved? And how much is falling above the cut point? That's all I'm doing. It's an assumption. I could put it at 3. I could put it at 1. I could put it at 0.5 and calculate it over. Does that make sense?
By above, you mean, all right?
Yeah. But technically, because I am a statistician, I have to tell you that there's going to be a very little bitty piece right down there that gets called 2. Though my graph doesn't show it, the distributions keep running all the way out. It's just so close to the x-axis. But yes, to the right. Yes?
So if you're looking at the top curve, there are 2, I know that's an example, but there will be 2 standard deviations. So we use.
Yeah, well, you said I'm not really very good at my fine motor skills of lining my green bar up at exactly 1.96 was slightly off. I got pretty close on this one, but I'm a little bit off on that one. I also made my bands bigger so that you could see the green bar, but technically it's 1.96.
If we use a difference of 2 standard deviations, would that give us more than 95%?
Yes, it would, but it's approximate. But generally, the basic rule is within 2 standard deviations. The exact calculation when you do a standard normal, plus or minus 2 standard deviations is not 95%. Plus or minus 2 standard deviations is 95.34%. You're being a statistician. Yes. Oh, my next question. All right. All right. So let me ask you this. Let's just talk for a minute. If I move it, I want to emphasize, if I assume there's a 3-unit difference, the green bars don't change because you're evaluating the data under the belief of the known. What's changing is where this distribution falls, and I moved it up to 3 so that the center had to be at 3. Then you've got much more area, and you're just driving your power up. But your comment, so if I shaded everything to the right, that's an approximation of the power. Yes, it would be almost right on top of the calculation. There'd be a fuzz factor that I got to add to the lower term. Okay? Questions? Hi. All right, that's where I'm going. Just bear with me one more minute, okay? Because what would you say? What would you say if I gave you the power to bend the curves? What if I made the curves tighter? I shrank them in. I have multiple levers. not only can I move it by the delta, I can make the shape tighter. That's your sample size. By increasing sample size, I can make it come even tighter and gain more and more. Okay? So there are multiple, you all right? Did I lose you? No, no. Okay. Okay. So we're going to get there.
I guess if you make it tighter, it doesn't quite fit to me. That area of the curve.
I'm going to show you. The actual area under the curve doesn't change. What is happening, I'll show you. Okay, bear with me. I got to get to the formulas. Let's just walk one through, okay? So here we go. This is the type of stuff I've got to sit down and do, and then I've got to be able to write it up. When we submit it to a journal, we'll write it up and send it. I'm going to have to assume a standard deviation. I've got to talk about how much things are spreading out, right? And I typically will assume that I'm going to go and do my jury trial with a 5% error rate. Okay? There's a 5% chance to begin with that I'm going to accidentally reject them all hypothesis when it's true. That tells me where to put the green bars. Okay? Assume that the researcher believes that at most the budget can afford is 30 per group. That's not the way it really works. That's the way it really doesn't work. It's not that I come to you and say, okay, here's your sample size. I actually start the meeting with, what can you afford? Before we start anything else, let's just talk about what can you afford? What do you think you can afford? And then let's me figure out where are we in the landscape and go from there. All right? Now, I'm going to warn you about this. I'm going to say, okay, we can go out there. There are plenty of online calculators that work pretty well. There's some that are not. Okay, so be careful. But I just wanted to be able to show you that you can go out there and do some rough out estimations if you want to yourself, but run them by a statistician. And also, if you're writing your own section, please let the statistician read it or a methodologist read it to make sure you got all the assumptions in place. You do not know how many times on study section, all I have to say is, I am the statistical reviewer. I regret to inform you that there are not sufficient details within this power calculation to allow me to replicate the calculation itself. Please resubmit. I'm brought in the room not to understand all the science. I'm brought in the room to say, can I do that calculation? And don't show some assumptions on there. They're not going to go. Okay? Now look what happens. So I enter the information. I have to tell them that I want a 2.5 difference in means, common sigma of 5. Let's say 0.5 or 0.5. Back up. You have standard deviation of 5. Alpha, and I say I'm going to fix my sample size at 30. That power calculation, which I will confirm, the biostats department actually pays, ready for this? $12,000 a year to give every statistician in the department access to the top of the line power calculation. And that's from the perpetual license. If they upgrade it, we get it immediately. So this is pretty much a 50-50 shot. You go at 30 with 30 people per group. This difference really does exist when you've got a 50-50 shot of getting a p-value that would say, reject them all, include the alternate. Okay? So right at 48%. What does that mean? Do the experiment 100 times. Do it 100 times. Do it identical, 100 times. 48 times, you're going to reject. 52, you're probably not. That's all the calculation says. It's a landscape. And then I wanted to show you what I would have to write if that's all I was going to give. Assuming a two-tailed hypothesis, notice I tell I've got 2 bars, using a type 1 error rate of 0.05 and a common standard deviation of 5, and a total sample size of 60, 30 per group. Provides power to detect the difference between the 2 groups, means of 30 and 27.5. Notice what I've done. I've laid out everything with the anticipation somebody else is going to try to come up with that number. I need to give them everything to verify. Okay. Now, let's just talk about going to the next piece.
I have a question.
Shoot.
So, that difference of 2.5, is that what you really expect is the truth, or is that what you need to see to believe that they're at least different?
Yes. I'm going to be smart aleck. Yes. It is both of those things. You would not conduct the experiment, would you, unless you believed you were going to agree with the difference. Right? Now, you want to target the smallest clinically relevant effect size that you can detect. So those are the two things. So yes, it is what you believe is going to be the truth, and it should be both relevant. Okay? It's just a teaching example. Two things that you have to ask yourself. What is the relevant one? Can I convince people to me? But you see what I had to do? I want to show you something. Here's assumption number one, the type 1 error rate. That's not too hard. I can do that. I have to be able to say I assume this. I have to assume how variable the data is going to be. Then I have to come in and talk about the difference between the two. Okay, once I've got those pieces, no, sorry, let's go back. Alpha, standard deviation, fixed sample size, and then a difference. 1, 2, 3, 4. That allows me to calculate 5. See it? That's why I say it takes a lot of assumptions. Alpha, standard deviation, group, and then the difference, then that. Now, being a good mathematician, can I choose to do it another way? Absolutely. I could say, you could come to me and say, David, I want the calculation done like this. We're going to use 0.05, we're going to use 5, make this 80, and keep this one the same. Well, which one will I solve for? And that's why people sometimes will come to me and say, David, I need a power calculation. And other people come to me and say, David, I need a sample size calculation. Are they different? No, they're not different. In fact, most times people, when they say sample size, they think they want power. Most of the time when they say power, they really want to do sample size. But I can take, and in fact, I can help you. You can come to me and say, David, I can only afford 100 people. This happened last week. I can only afford 100 people, David. 50 per group. I said, all right, if these are the assumptions, can you produce this difference? Do you think that difference can be produced, and do you think it's clinically relevant? And we had that discussion. And then I varied the assumptions to see the range. That's what a power calculation really is. Okay, I know it's complex, but it's really not that complex. If you keep that picture in mind, all that, go back to that picture. Interesting. It's leaking. If you go back to my picture, all those assumptions are really talking about the spread, how much they bell out, and controlling where they fall in the shape of it. That's all it's doing. I think you actually need it up here. I'll just leave it on the coaster for right now. Whew, I'm glad Brian would be mad at me. I did not get his nice equipment messed up. Brian, are you listening? All right, look at this one. Okay, notice moving the means increases the power. Look what I did here. Okay, I just did another calculation. I kept type 1 the same. I kept standard deviation the same. I kept my sample size the same, but I moved them further apart. As I move them further apart, this has to change. It goes up. Okay. I move them further apart. Okay. There's another way I can do it. I can also increase power by assuming that number is small. If I make that number smaller, power will go up. If I make this number go up and keep it within the same, power goes up. I've got multiple levers to pull. But what we have to do is we have to have that discussion of what's the meaningful difference and then what are the reasonable assumptions. Yes?
2 questions. My understanding is the general accepted power is 80 or 90, depending on how strong your player data is. Look like. Can you describe that?
All right, so that's a great question. I would have paid you money. I would have paid you money to ask that.
Please.
So it's a true statement. The threshold that people typically say is you need to have at least 80% power before you go to try to do this experiment. I have really pulled myself away from that. When I design large trials, or when I'm going into NIH and say, hey, can you give me 1 million? I don't put it down at 80%. I pull it up to like 85 at a minimum, or if I can, if the budget can afford it, I bring it up to 90%. Because think about it, I've warned you, I am making a boatload of assumptions. So if I increase my power and I'm targeting the sample size that should give me 90%, I've got a lot of wiggle room. Some of those assumptions could start being off significantly, and I'm still in the safe range of 85, 83. So typically, I will, if it's a tight budget, I'll try to keep it at 85. If I can, I bring this up to 90. But generally, NIH is going to be okay as long as you convince them that you're at 80. Where that rule came from? Pretty much where 0.05 came from. Out of the air. Okay. You get 2.
The reverse is, so let's say you have a retrospective study, and you have a known N. You got,
yes.
Is it meaningful if you find or don't find a difference to do a power calculation?
Gosh, now we want another brilliant question. Are power calculations useful for retrospective studies? The answer to that question is yes, before you let me start doing the analysis. In other words, you come to me and you say, okay, David, this is what we're doing, this is what we have. It's imperative for me to sit down with you before we do anything and say, okay, what's going to be relevant? What do you think is going to be relevant? And we can do that calculation and do it before the whole thing starts. And then be able to say, prior to doing the actual analysis, we have this data set, we're going in here to look for this. And if it exists, we would have 80% power to do it. Okay? That forces the clinically relevant piece on you before I do anything. What goes wrong in the journals, and I spend at least 2 days a month fighting this. Somebody's done an analysis, and it's not significant. And somebody goes, oh, that's because you're underpowered. That's always the fault. That's a meaningless statement. You can't talk about power without first talking about what's clinically relevant. And people will come in and say, well, we're going to do the retrospective power calculation, and we're going to use whatever the data set gave me and ask, what's the power to find something? Why are you handing that privilege over to the data set? That's a clinical judgment. And I've had to write plenty of sections to say it was it is a null trial. We did not do this. However, we a priori were looking for this difference. If that difference existed within this data set, then we should have had an 80% chance to get it. The fact that we did not find it indicates that it's likely not of that magnitude. So,
but in most retrospective studies, we already have the sample size.
that's exactly right. But you're exactly right. The sample size is fixed, but the clinical relevance is the difference is not fixed.
Okay. So in order to get the power that we need, I have to tweak it with
Yeah, well, or we need to have a discussion of it.
Okay.
I am being recorded. Okay? I had to review somebody's retrospective study the other week, okay? I read the assumptions and I had to email them immediately and say, hey, well, before you go any further, let's sit down and talk. You're not going to have agriculture. You're not going to have agriculture. Because there was a dichotomous outcome, yes or no. They were going to survey 200 individuals. I was predicting there were going to be 2 people who had the disease. You're not going to be able to do anything. So just because it's retrospective does not mean power's off the table. You can still do an investigation and ask yourself, given I have 100 individuals, what is detectable with reasonable power? What is not detectable? Or what would you not expect to be able to find with a good power? It's still, remember, it's always just studying the landscape. Yes?
So with regard to practical relevance, for one, in terms of patients, one outcome might be acceptable for one patient and one might not be for the other. So you just report the power and then hopefully people understand that it's for them to interpret.
All right, we got to remember, I know this is a great, gosh, we're not going to get through all the slides, just going to tell you up front. We are asking great questions. I'm here in 2 weeks again. We can continue to discuss these other things, and I'll try to set up the time. We're not going to make it through everything. I'm sorry, I've got a hard stop. Sorry. Keep in mind, when I do an experiment, this is going to sound so cold. It's going to sound so cold. I'm not cold. I don't study individuals. I study big group. I can only talk about what's going on average. I need multiple people having the same outcome. Okay? So what you said is this outcome may be more relevant for this subgroup of patients and this other outcome for another. Fine. I designed my experiment to have both. And I will power both. But I have to measure that outcome with everybody in the study. Does that make sense? And that's what happens when studies get really complicated. When I have well-meaning clinicians who come to me and say, I got 4 outcomes, 1 primary, 3 secondary. But this happens all the time. Whenever I do a phase 2 clinical trial, I'm studying efficacy. I want to know, do I have preliminary evidence that this drug is effective at relieving your migraine? Yeah, that's the outcome. Do I fail to measure toxicity? Of course I don't. I always have toxicity, but toxicity measures matters to people also. So, but the more power calculations you put in there, the more complex. So I've got to go to the sample size that covers the least, the hardest, the smallest difference. The smallest difference will drive the largest sample size. That's the one I've got to use for all my companies.
Can you do this with nominal data? Because it looks like you
I can do anything.
Okay. Love that.
I'm serious.
Well, because it doesn't seem like you can use nominal data if you don't have a standard deviation.
Oh my gosh. How much do I owe you?
Nothing against that.
Okay, one more real quick, and then we get to your example. Okay. This is the third version of the calculation. This time, I said, no. Y'all are adamant. We're going for 2.5. It's going to be a 2.5 difference. That's where we're putting our flag, David. Okay. And David, give me 80% power. Well, wait a minute. So we put in the alpha, we put in the standard deviation. You fix this. You fix that. What's the one that's left to bury? There you go. That's the way it's really done. I come back to you and say, for 80% power, you need 64 per group to get that difference under these assumptions. Okay? And all of this is just really imagining curves. All of this is just imagining curves. All right, back next to the really good keys. What about proportions? Because not all data is proportions. Yes, no. But you are my best friend, but your worst enemy when you come and bring me nominal data. You're doing me a great service because I don't need a standard deviation. If you give me the proportion from statistical theory, I can get everything I need. I don't need the standard deviation. You come to me with a continuous outcome, you've got to bring me the clinically relevant difference and a standard deviation. You come to me and say, we're studying yes, no. So, classical. We withdrew a medication, we felt like huge to the bones, that you had a reservoir in your body. The primary outcome was fracture within 3 years, yes or no. Follow you for 3 years. Did you fracture, yes or no? Yes or no? Yes or no? It's not yes or no. It's going to be proportion. How many in this group had a fracture compared to how many? I don't need a standard deviation because statistical theory gives me the standard deviation. It's fixed. It's a function of the proportion itself. For proportions, stating the proportion also provides all information for standard deviations. I'm all free. Once you give me the proportion, you came to me and said, I think 80% in this group is going to have the event, 50% in this group is going to have the event. I turn the computer on and we go. That's all I need. But you are your own worst enemy. Let me finish it. You're my best friend, but you just hurt yourself. Sample sizes for yes, no, always much bigger studies than if you have a continuous outcome. Yes?
So how about I know that I'm not going to obtain and take for sample size in both slides?
I can do that all day long too. You want to come to me and say, David, I want to put twice as many on this drug compared to this drug. I can do that. I can do that. There is nothing requiring me to make equal groups. It is just the most efficient with regard to the number of people. But if you have a justification that we can use, we can unbalance the design all day long. What else? So what it looks like here, so here, again, my teaching example. Now, if you can do yourself one favor, if you can think about this, you're always going to be safe with a power calculation when you come in and you say, hey, okay, he's going to do proportions now. Let's assume 0.2 and 0.2. What do I want to happen under the alternative? Okay, I'll keep one at 0.2. I'll move that up to 0.3. Right? Talk to me. What if it went from 0.2 to 0.4? Bigger or smaller? Bigger, difference. What happens to my sample size when it goes down? What if I wanted to go 0.20 to 0.22? Please don't do that. They're closer together. What's going to happen to your sample size? Notice something. Let's say we wanted to say 80% power, 0.05. I can immediately tell you you're going to need 588 people all together. Two-group design, but you got to get into a sample size of almost 600 people to spot that difference statistically and give yourself 80% power. You can see in my teaching example, I'm always anchoring. Let's not go below 80. Let's not go below 80. But if we were writing a grant, I would build a table and show where 85 is, okay? Wrong way, David. This is what I really do. This is what I do, okay? This is what I would hand you if you came to me and said, we're designing a future study. I would give you this table. I would say, if you're unsure about the standard deviations, it's okay to build and do multiple. So going back to my example, I believe what I have here, this is my teaching example. Yeah, this is my teaching example here. Let's assume 30 per group. You came to me and you said, David, we're going to be able to do 30 per group. I would come to you and say, okay, let's look at this. Here's my standard deviation. What happens as my standard deviation goes up? Power always falls if my standard deviation starts increasing. So you see that if you assumed 2.5, but you actually had twice that, you're going to fall from 97% power down to 48% power. It's very damaging. Okay? But what if you start producing a bigger effect size than you thought? Well, the bigger the effect size, higher the power. So for this situation, if you were talking about 30 per group and you thought clinically relevant difference would be 2.5, your standard deviation would be 5.0, I would tell you you're 47.8 or 48% power. But if you actually produce a bigger effect, you would jump up to 76% power. Now, this is really not the best teaching example because really, down here, this is telling you this row is not feasible. If this is your set of assumptions, if this is really what's going on, you got to get off of 30. 30 is not, you're not going to survive on 30. Here, all right, if you're getting up into a range of 3.5 to 4.5 between the groups, you're getting in a safe range. You're getting close here, but you're really not over the line. We just worked out 0. And there's nothing to stop me from doing 2.5, 3.0, 3.5, or I give these tables to people and say, let's discuss this out. That make sense? Yes?
So where does 30 come from? Is that the one that Cohen did?
Yeah, well, yeah, that Cohen did some, I'm a big fan of Cohen's one. He's fallen out of favor over the past several years with statisticians, but I still like what Cohen did. The 30 is just my teaching example. I just said, suppose you came to me and said, David, we're stuck with, I want you to start talking about 30 per group. Can we start our discussion under that belief? What can you show me what the different power ranges are? And that's what I would do. I'd come back and say, this is my first grid, let's talk about this. And I would probably be at this point saying, can you get to 40? Can you get to 50? And see if we can do the same size up. All right? All right. Why the calculation's not that important? Can I tell you the truth? The study sections really look for the fingerprints of a statistician or a methodologist. They want to see that you're doing team science. One of the tells that you have been working in team science is that it reads like a statistician wrote it. The statistician has put all those key pieces of details in place. Okay? So especially for grants, it's important that all the assumptions are listed. Okay? It's an easy thing for people to say, I don't believe your assumptions. That's one thing. It's an easy thing to do, but once you produce the grid, you take that argument off the table because you showed all possible assumptions. One thing you can't take off the table is, I can't recreate that. That's the biggest danger. It's something that can't be recreated. And just have, even if you do it yourself, and I'm a huge fan of people who come in and say, David, this is my first table. I did it myself. Can you, with your laptop right there, can you redo it and double check it and help us write it up? But all because that way, two people working together is always better than one person working alone. Okay? All right, I think that got me through half my slides today. Yeah, that's it. I'm going to leave the other ones to you because it's the exact same story. I want you just to look at them. We'll be back. Well, I don't think we meet next week. Next week is spring break, right? Y'all meeting next week? Y'all know y'all meeting next week? I don't think we are. Okay. Then I think I'm back again for rigor and reproducibility. And what we'll do is that talk is clearly just an hour.
Pretty triggers.
I don't know who they are. But we'll discuss them and we'll go through it. The only thing that changes, look, you can remember those bars. It doesn't matter if I'm doing regression. It doesn't matter if I'm doing ANOVA. It doesn't matter if I'm studying correlation. It doesn't matter. All that changes from test to test is the shape of the curve. That's all. But it's always the same game. Power is shoving the curve or altering the shape of the curve under a belief of assumptions in the alternative. That's all it is. All right? So they didn't give you all the bridge. I don't know why they didn't. If y'all like to fire me for giving you some time back, I'm open to it. All right, sorry guys, I have to adjourn early. Yeah, my phone was getting blown out.
Yeah.
So unfortunately, I'm not going to be here the next time.
Sorry, I'll sit down, honey. We'll go to email and get a cup of coffee and we'll go through it all.
Oh, sure. I would love that because actually, I don't know if my brain just spazzed and was like, if you get this slide and you got it, and it's like, because I felt like I was following you up.
Sorry about that.
And then I'm like, what is it?
Be ready.
Okay.
USB.
Okay, great. Thank you.